Welcome to the Pei Lin Lee Travel Award Lecture. The Institution of Structural Engineers is and always has been proud to play its part in fostering new talent within the field of structural engineering. The Pei Lin Lee Travel Award offers opportunities for young engineers to explore their interests, obtain professional development, and inform the industry on innovative practices. First awarded in 2007, the Pei Lin Lee Travel Award continues the institution's commitment to young engineers. Grants of up to £3,500 are awarded to members who wish to spend 4 to 6 weeks abroad studying current practice or trends related to the use of any construction material in the field of structural engineering. The award encourages a particular focus on the study of innovative materials and construction techniques and aims to bring these to the forefront. We are always grateful to Pei Lin Lee's family for their continued generosity. Via this grant, young engineers are provided with an unrivalled opportunity to sample the technical, economic, social and political conditions in another country and to examine how these factors affect the practices of structural engineering. This opportunity enables young engineers to broaden their experience and allows the institution to share their research with the structural engineering community via this annual lecture. Arthur has been working as a structural engineer at Price Myers since graduation in 2013, and he became chartered in 2019. He has served for several years on the iStructE Structural Futures Committee and is currently their Vice Chair. In this role, he joins other committee members in blue sky thinking to explore advances in research and technology from a wide range of fields that could influence the future of structural engineering and advise a global iStructE membership. Not surprisingly, this committee works hard to consider how engineers can tackle the climate emergency, and Arthur shares the global concern for the impact of the construction industry on the environment, and he wanted to investigate how timber may offer a solution to reduce CO2 emissions and lessen the effects of climate change. In 2019, after an exacting process that required written submissions, budget plans and an interview, Arthur was awarded the Pei Lin Lee Travel Grants for his proposed investigation of tall timber structures. His aim was to investigate the drivers and innovations enabling timber construction to compete with steel and concrete at scale, identify potential obstacles and environmental challenges, and also to explore the future of engineered timber systems. Within the context of rapidly evolving regulations surrounding tall building design in the UK, Arthur travelled to Canada, the USA and Norway to explore the perceived differences in regulatory frameworks. On his travels, he met with engineers and architects and researchers and with manufacturers who have been crucial in developing the tall timber building market. He also studied the drivers for the development of tall timber buildings in these countries, the preconceptions about the use of timber, and he learned about the technical challenges that face the tall timber structural design. This covers a wide-ranging but very important topic of recent discussion for the institution, so we look forward to him providing an insight into his findings during his lecture now.
Thanks, Jane, for the introduction, and hi everyone, thank you for joining online. So I'm going to start by looking at the context around the study, then move on to North America and then Norway, and then I'll provide a brief overview of the fire safety design in these regions, which is a really important topic of discussion. We've only got around 20 minutes for this presentation, but a full report will be on the iStructE website, hopefully answering any questions you may have. So first of all, why should we be studying this now? Let's just remind ourselves of the context. Well, 2019 was the year that we declared the climate emergency. The embodied carbon of structures is one of the largest contributors to global climate change, and this is rapidly becoming the defining issue of our age. From the IPCC report, we now have 9 years to limit global warming temperatures to 1.5 degrees Celsius to nullify the permanent devastating effects of climate change. And as Greta Thunberg declared recently, the deciding factor for every new development should be the resulting carbon footprint. We know that the production of cement and steel accounts for around 15% of global CO2 emissions, whereas timber has the ability to sequester much of its captured carbon, or at least result in a reduced carbon emission depending on its end-of-life scenario. So the UN predicts that 70% of the global population will be resident in urban areas by 2050, which amounts to around 2.3 billion more people than today. And as engineers, we have to find new ways to design and construct buildings to meet this demand, whilst also reducing CO2 emissions and maintaining biodiversity. And then, of course, how can codes of practice keep up with this potential systemic change in the way in which we use this material? Timber has always seemed to evoke a more emotive response compared to its competitor materials, and often cited are issues with fire safety, robustness, and durability. But how can we move this debate on, and what further research is needed to better inform our designs? And now tall timber is making the headlines, as you can see here. But what is the public view of tall timber? Ultimately, they are going to be the end user. It's certainly an uncommon material to use at heights, but is it strong enough? Is it stiff enough? Is it fire resistant? As engineers, we have to be able to give easily communicable answers to these very difficult questions. Unfortunately, I'm not going to have all of these answers for you today, but hopefully will offer you some really useful insights from my travels to these regions. So moving on to tall timber in North America. So I'm going to start off by going back to basics. What is mass timber? Well, this is a collective term for engineered timber products such as cross-laminated timber, CLT, glue-lam, or dowel-laminated timber, DLT. And these are effectively solid timber elements comprised of sawn timber that are glued or mechanically fixed together to create a stronger, stiffer element. And these are the material systems that I'm going to be focusing my research on. So what's going on in North America? Well, in December 2018, the International Code Council, ICC, introduced changes to the upcoming 2021 International Building Code, allowing the prescriptive design of mass timber buildings up to 18 stories without acquiring special permission from the underlying authority. So before this, there was no guidance for mass timber buildings above 6 stories, and any proposed building had to undergo a performance-based alternative approval process. So what this offers is a relatively straightforward route to compliance for these types of buildings. And this has already been adopted in parts of North America, especially the Pacific Northwest. What are the drivers for building taller in timber? Well, there are certain economic reasons. Canada effectively has an unlimited supply of timber, and through sustainable management, its rate of deforestation has been close to zero for the past 30 years. And the hope is that this surge in timber usage will help catalyze the lumber industry, thereby boosting local rural economies. Carbon, Canada and lots of US cities have pledged to be net zero by 2040 or 2050. Thereby, the thought is that using sustainable forestry and mass timber usage in construction, this will then act as an agent to help achieve this. And then urbanization. Many West Coast American cities are run by socially liberal parties who are looking to use cheaper local materials to help improve affordability and boost social housing projects in a sustainable way. So the foundation of my research was meeting with various engineers, architects, contractors, and researchers to learn about the technical aspects of tall timber. And a list of case studies, a full list of building case studies is contained within the report. However, I'm going to focus this presentation on 3 today, highlighting the pertinent points and hopefully giving you guys a quick flavour of what is going on out there. So, Brock Commons is one of the most important tall timber structures over in Canada. It was born out of a research program launched by the Natural Resources of Canada, NRCan, to demonstrate the legitimacy of tall wood structures. It's what we call a hybrid building with stability provided by reinforced concrete cores. It's a student residential building with the grid set to suit the width of the CLT panels at around 2.4 meters. And it's essentially a flat slab analogous structure with the CLT spanning in 2 directions between point supports, which are glulam columns. So in this next slide, you can see it in a bit more detail, and you can see there's a really neat column-to-column detail, which helps reduce the shrinkage-induced stresses in the panel around the point of support and helps isolate the vertical load. So the next building is called the PMX Building, which is formed from the Sidewalk Labs development of Toronto Quayside. Sidewalk Labs are the urban development arm of Alphabet, who also own Google. It's a prototype mass timber building formed of a catalogue of different components that make up this 35-storey building. It's what we call an all-timber building, with all the main structural elements made out of mass timber. And you will note that this is that quite a few projects on the case study list pride themselves on this fact. The columns are pretty massive, in contrast to Brock Commons, and they're exposed and designed for charring. The stability is provided by an LVL diagrid, but it is also the first proposed use of a tuned mass damper for a timber building, which is required because the building is just so lightweight. There are lots of high-level studies that have gone on to work out the effect that this tuned mass damper has on the dynamics of the building, as the effects are largely unknown up to this point. Unfortunately, the Toronto Quayside plans have gone on hold. However, I think this is a really exciting case study. And also, the growth in mass timber isn't just synonymous with tall buildings, but also different typologies, like this commercial development for Adidas, forming the new North American headquarters in Portland. It's a collection of 3 to 5-storey buildings on a 45,000 square meter development, so a huge site. I was lucky enough to visit it on site while it was being built. And you can see the interior space looking really fantastic. It's got these a really nice typology with 2 glulam beams that span between columns, offering a really nice double shear connection, and a rib cassette floor that spans in a different direction. It allows you to change the facade as you go up the building, or for the structure to cantilever in both directions. So just moving on to the evolving economic agenda. Well, mass timber production is still very much in its infancy in North America. There was massive growth last year. However, there are still only a handful of projects, and there is certainly a lack of experience and expertise in constructing and contracting mass timber buildings. There are only 7 CLT factories in the States at the time that I visited, compared to around 30 in Europe. However, there's a new wave of finance and investment moving into this area. For instance, 90% of certain forest in Canada is publicly owned. However, it's leased to only 3 companies. What these companies are doing are building mass timber factories to help vertically integrate their business, and the hope is that they would be the only ones to supply in these different regions. And there was also lots of disruption by tech companies. So I mentioned Sidewalk Labs. There's also a company called Katerra, who were last year valued at $4 billion, who are moving into this market and sense a big opportunity here. However, the impact on timber supply is likely to remain unchanged. Oregon, which is more or less the same size as the UK, has 50% forestry coverage compared to about 10% in the UK. and lots of these trees are species that are widely available for CLT production. So moving on to Norway. The reason I went there was to see the tallest timber building in the world at 85 meters, which is Mjøsbandet. It is an exposed, it has an exposed mass timber frame formed of glulam columns and a glulam diagrid that provides stability around the perimeter of the building. Some of these elements are 1.5 meters long at the base. It has a core formed of CLT, but these do not provide stability. Here are some photos from the interior. Lots of dynamic analyses went into the design because it was so lightweight, and actually the top 7 floors needed to be precast concrete in order to provide that dead weight and limit the lateral response or sway of the building. And having been to the top, you can actually feel the building move, and this is backed up by data from an accelerometer that they installed at the top. I've put together a list of considerations that affect tall timber buildings from my research, and these are split into the vertical and lateral design. Essentially, many of the design issues associated with tall timber buildings are just exacerbated at lower heights, and certain issues to do with differential movement between differing material systems need to be carefully thought about, especially the short-term elastic case. I've also provided a summary of the core properties between main materials, which I think is useful to highlight 2 points. I'm sorry if this is going to sound extremely basic, but I think it is a helpful reminder. But firstly, timber is less stiff. So mass timber elements are around 20 times less stiff than steel, and shear deformation can cause a big issue with tall timber buildings. The second thing is that timber is less strong. So certainly if you have an element that has a lot of bending, this can result in significantly larger elements that you would get with concrete and steel buildings. So although you can use timber in tall buildings, you're just going to use a lot more material, and certainly at the early stage of a project, you need to be really careful with coordinating this with the architect and the client. So the next slide is a very broad overview of the European or UK codes compared to North America. So this is fairly generalized, but I wanted to highlight 3 different things. So from a regulatory point of view, in the UK, on the whole, we can design any building in any material in any way we like. We just have to demonstrate it's suitable. Whereas in North America, things are a bit more prescriptive. In terms of the design procedure, in the UK, CLT is deemed an innovative product, and therefore the design procedure is set by an ETA process and can vary between suppliers. In comparison to the States, there is the PRG 320 code, which has helped to unify the design of CLT, so the requirements and design procedure are all in one document. And then fire design. Well, in Europe, it's not particularly straightforward, and again, it can vary between the supplier. In contrast to North America, it's slightly easier and follows similar principles to Eurocode. However, it potentially lacks the development that the European codes are looking at currently, which I'll move on to now. So at the same time as the IBC changes were introduced at the back end of 2018, the UK introduced a prescriptive change to the building regulations, disallowing the use of timber in the external wall build-up above 6 stories for residential buildings. So clearly a dichotomy exists between North America and the current direction of UK regulations. This is probably the most significant topic for tall timber building design, and unfortunately we haven't got enough time to go into depth here, nor am I from a fire engineering background. So for anyone who is interested in learning more, I would highly recommend reviewing information put out by the University of Edinburgh team recently. People such as Angus Law, Luke Bisbee, Danny Hopkin, who have provided a really good insight into these issues and concerns raised raised by the engineering research community. What I'm going to do here is present a very high-level comparison of two contrasting regions, and my report will go into a bit more detail about this. So the first difference is that many issues were identified quite a few years ago with delamination of CLT due to heat in the adhesive, which can result in cyclic burning in compartments. PRG 320 tries to identify and exclude delamination with the specification of more heat-resistant adhesives. So although this can't be eliminated, it can be delayed. Secondly, in PRG 320, temperatures cannot exceed a particular value during the decay phase of a fire. This is an area of major research for certain high-risk buildings that need to ensure auto-extinction during a fire scenario. The research for a lot of these American codes are based on more compartment fire tests that help to ensure burnout without external intervention for the highest risk buildings. And just from a regulatory point of view, although there are a variety of local, state, federal codes and approval processes, the prescriptive nature helps to clarify some ambiguity that maybe exists in European codes. Whilst also in British Columbia, there is also an alternative approval process. For instance, also in Vancouver, a code consultant is a mandatory design member who is someone from a technical background who helps to manage the fire strategy during the design process. So just moving on to the recommendations for the UK, I won't go through them in detail here, but more on this can be read within my report. The main point is that there is now a specialist interest group within the UK through the Structural Timber Association, STA. They are dedicated to the design approval process of mass timber structures in medium and high risk building scenarios, and that's run by Danny Hopkin. I think some really positive things will come from that, hopefully sooner rather than later. The important point is that there are risks with exposing mass timber that you don't get with concrete. So if you're unsure, advise encapsulation with fireboard following the recommendations of the supplier, and seek advice from a specialist in fire engineering of mass timber elements. So just moving on to the conclusions, well, there was a recasting of the boundaries in the way in which we design and use timber, certainly in North America. We should consider new typologies for mass timber buildings that have traditionally just been steel and concrete framed. And we always need to consider the risks with the structural fire design when we're exposing timber. The next couple of slides are rehashed from a brilliant lecture by Alan Dowdall at Ramble, so full credit to him, but I thought he made a really clear and important point. And that is, what do we mean by tall? Is it total building height, which may be a building like Burj Khalifa, or is it the slenderness of a structure? So just for comparison, this is where Mjostane sits, clearly right at the bottom end of the scale. So I think we need to be thinking about materials in different ways. So just finally, I believe that tall timber is a phenomenon. I think it's one that is likely to be short-lived, but that does not take away from viewing these projects as demonstrations of the capability of mass timber and them acting as catalysts to encourage the wider acceptance of timber buildings, especially with the public. The real win for mass timber is medium rise, and timber should be taking a greater share of this market. I often hear people say all housing must be built from CLT. I think this is wrong. Don't think it's too simple to design a timber joist or a cassette floor or a stud frame. If it doesn't need glue, then don't design with it. Half of the embodied carbon in CLT is through the production of the adhesive. So just to back that up, 90% of housing in North America is timber stud frame, and there are really obvious reasons why from a cost and carbon perspective. And just remember, 99% of the existing building stock in the UK is under 6 stories. So we should be using more timber for these low-rise buildings. Finally, just referring back to the material properties sections, we need to use the right material in the right way. So the way forward for tall timber structures could be with hybrid buildings. So potentially looking at a steel frame with timber floors, or maybe even a timber frame with concrete cores providing stability like Brock Commons. These will offer the lowest embodied carbon options. So thanks again for joining. I hope you enjoyed it. Please get in contact if you have any questions or want to discuss anything further. Thank you.